So taking a look at this similarity as a concept, okay, we have to first think about what geometry is as a concept, okay? So a little bit of wordplay here. Okay, first of all, this is what the curriculum says. This is what you will be tested on at the end of the unit, and what you'll be tested on the final exam that, remember, is worth 20% of your mark, okay? Let's keep it simple. I'm not going to read the whole thing to you. You need to determine the surface area of a 3D object, and specifically a composite 3D object. I'll explain what that means as we go on, okay? But focus on those first words, just surface area. You got to figure out surface area, okay? As well, you need to understand similarity of polygons. So you need to know what that word means, similarity, and you need to know what polygons mean. So as I said to you guys last week, a lot of this is about understanding the words, so you know what the words mean. So let's dive into this, okay? Let's open up with just a basic discussion. One day you guys are going to go out and buy your own apartment, or rent your own apartment, or one day you may even go out and buy or build your own house. And what you may know is when you go to look at a house, they have these things called blueprints or scale diagrams that look something like this. In a similar vein, if you've ever been to the Manitoba Museum, or when you were in elementary school, you made dioramas, small little versions of, like, say, this ship battle, or like a farmyard or something like that, a diorama. In both cases, those things are what are called scale models or scale diagrams. My question is, what does the word scale mean in this context? Why is the word scale even being used? It's not like a scale on a fish. Brian, what do you think?
It's a smaller scale version,
I know, but you're using the word scale to explain the word scale. Yes.
It's a smaller version that allows you to see the entirety of what you're trying to show without it being gigantic.
Right. Like there's no such thing as a life-size map of the world, right? Because that would be the world itself, wouldn't it? Yeah. So you get what I'm saying? Like, in order to show a map of the world, they had to make it smaller. They had to, quote, scale it down. So in this context, the word scale is the changing of an object by a number, right? Like, for example, you could say it's half as big. Half is a number, right? So you're applying mathematics to real-world objects. And that's important to think about, okay? So, because when you think about the word geometry, what it actually means is in ancient Greek, it's from the word geo, which translates as earth. That's why you have the study geology. And metron, which translates as measurement. So it literally means measuring the earth. That's what geometry means, okay? It's a branch of mathematics which looks at shape, size, position, and spatial proportions, okay? Again, to keep it simple, geometry is taking numbers and putting them on objects, right? I mean, right now there's a number on the shoes that you guys are wearing. It's your shoe size. That number was put on that object for your benefit, okay? You guys are probably basing a number on your height and your weight and things like that. That's putting numbers onto real-world objects, okay? And in math, we know we can manipulate numbers. That's what math's about, is changing numbers and doing stuff with the numbers. So if we change the numbers, do we change the object? No, but it's kind of interrelated. Simon? What? No, you're fine. You're all good, okay? One of the questions that we often have in mathematics is how do we even put numbers on an object? Like, how do we define it? Why is that number 7 or 6 on your shoe size? Like, what does that even mean, right? And is that the only way, right? Sometimes when we go buy a coffee at the store, we don't need to necessarily buy it by number. We can use fancy words like large and medium large, or when you go to Starbucks, what are the 3 sizes at Starbucks? It's like venti. No, not at Starbucks. It is not. Who knows what you call it? How do you order at Starbucks? How do you order them? Grande, venti, and tall. I always was like, my wife still will make me order at Starbucks because she doesn't want to say the word venti. But how else, right? And is the definition we use enough? Like when you hear your shoe size is 5, Is that enough to work? Maybe not, okay? So does the definition let you imagine what the object looks like?
Sometimes.
Sometimes, but sometimes it needs more. So let's just think about what that, let's imagine a circle. What makes a circle, right? Right? Well, one thing you think about is things that are circle-shaped, right? Like my head, right? So, and that, yes, that's my actual head in that picture, right? But if I was to ask you to define what makes the circle a circle, you'd probably use words like round and circular, which again, isn't quite defining it properly. What do you got, Simon? What's that? What has no edges? I like where you're going with this, but a circle has no edges. So it's a shape with no edges. Okay? Tynan, what do you think? Okay, 360 degrees from what to what? Simon, you got a definition? Yeah. Does it have edges? Okay. It kind of, yeah, it has one edge. Maybe you could think about it in terms of, yes? No straight lines, okay? I think you guys are definitely in the right ballpark. You're definitely giving great descriptions of the circle. I could say maybe what you could do is think about a ladybug, okay? Walk in a path, okay? If, for example, the ladybug walked along the edge of a spinning desk, right? And formed a path, like pooped every time it walked a step, those little dots would form the shape of the circle, right? It would form that. Could we say something about every spot on her path? Like if we picked one spot on that path, is there a way we could measure that spot? Well, maybe we could measure the distance from the center of the circle to that dot, okay? Maybe we could measure the distance between the dots. Maybe we could measure the distance from one dot to a dot directly across the circle. There's different things that we could use to put numbers on the way we're defining that circle, okay? I mean, we can even notice that every dot along her path, and I said her, right? Isn't that kind of sexist? I mean, can't a ladybug be a male? I think it can. Every dot is the same distance to the center of the circle. So there's some things about the circle that are quantifiable. We can put numbers on them. This is a word that you don't have to know, but the path is called the locus of points, okay? So a locus is a plane or a set of points that satisfy a given condition, okay? Locus, by the way, is related to the word location. That's where it comes from, right? So a locus, for example, if I said, give me all the points that are equally the same space between line L and line M, could you put a bunch of dots that are equally in between those two lines? You'd probably draw something like this. We'd have all those dots there in between. And if you made as many dots as possible, you'd essentially be drawing another line in between. And then we might use words like parallel lines that maybe you've encountered before. Okay, so some words come into the geometry there, but really it's just about sort of finding a place in the sort of real world with the numbers and how they apply. Okay, so locus, okay, the plural of which is loci, is a set of points or path that conforms to a rule. Okay, so locus can be very undefined. It can be one dot. It can be a curved line, which is essentially a whole bunch of little dots. It can be a straight line, which is also a whole bunch of little dots. And it can be a whole region. And if you think about it, that is really just a whole bunch of dots. Dots that are kind of right beside one another to create that. I mean, if you had to paint this wall, and all I gave you to paint it was a Q-tip, and I told you you couldn't swipe the Q-tip, all you could do is dab the Q-tip on the wall, you could paint it if you had enough time. It would be boring, but you would just keep hitting dots until the whole wall was painted. And then if I asked you to count the dots when you did it, you probably could do it if that was your assignment. I won't make that your assignment, but let's say it was. It kind of proves my point that the way we visualize things is in terms of sort of groupings and values. All right. Consider a single point. This is a zero-dimensional object. It has zero dimension to it. It's impossible to measure a dot. It's just a place in space. I can't measure anything about it really for the most part, okay? But if I have a second point and I connect them, now I can measure the distance between the 2 points. So now I have one dimension. I have length, right? I now have one thing I can measure. One thing I can put a number on is length. And that's a one-dimensional object. But one-dimensional objects are also not that practical. So often what we do is we add a second point, okay, or pardon me, a third point, or a second line. And now what had length might now also have a width, okay? So now we have a two-dimensional object, okay, because it not only has a length, but it also has a width. Now with this, I can measure two things. I can measure the length and I can measure the width, but I could even measure something else. I could put a number on how many dots it would take to fill this. And we usually call that area. The area is the amount of stuff to fill this. So if I was a painter, area would matter to me because I'd need to know how much paint I'd need to paint, say, a side of a barn. So I'd measure the barn so I know approximately how much paint I'd need to buy. Or if I was wrapping a present for Christmas, I'd know approximately how much wrapping paper based on that. Now sometimes we do this just by eyeballing it, but obviously we can put a lot more thought into that if we put the measurements and the values to it, okay? Okay, so now we add the third dimension. Yes, Simon? Yes. The third dimension is the easiest for us because we live in the third dimension. That's where we exist every moment of our lives, is in the third dimension. That's what you guys are looking at me right now, okay? To add the third dimension, we add a depth to it. So we have length, pardon me, width, and now depth to this. This is now a three-dimensional object. This is the real world, okay? So we can measure all three of those. We can measure length, width, and depth. As well, we can also measure the area of each side of this. So if this is a piece, if that cube was a die from a dice, I could measure how much white paint, if I didn't have any dots on it, would go on all 6 sides of the die. I could measure the surface area of all the sides, okay? And that is the surface area of a three-dimensional object, is the surface area of all the visible sides, okay? If we wanted to as well, we could also, if this was a glass cube, we could pour things into it, okay? Which is essentially what's called its volume. Now, volume is not something we're going to cover in this unit, but again, I hope that it's something that you've seen in the past. Okay, so some of this unit you're going to be drawing 3D objects, okay? It was actually a much larger part of the previous grade 9 course, but to do this, you kind of need to think about how you're drawing it. Are you looking at it from the top, or from the front, or from the back, or from the side, right side, left side, or from the bottom or the base, okay? Each of those ways you look at something affects the way you draw it, right? For example, looking at a building as you fly over it in a plane, you would draw it very differently than if you were standing right in front of it, okay? If you're on the left side of it, something, right? If you're looking at a person on the left and they're facing forward, you're going to, again, draw them very differently than if they were in the front. And similarly, if you're looking up from the bottom, you will also draw something differently, okay? So this is something you need to think about. Now, the objects you draw would be fairly simple, right? So here's an example. Here are 4 views of an object. So it looks like this from the front, this from the right side, this from the top, and this way from the base. And all this thing is a bunch of little cubes put together. This is what it would look like, okay, in 3 dimensions, okay? Because if you think about kind of how that relates, you can maybe visualize it. Now, here's the deal. With some people in this room, they're going to find this kind of thing really easy. Their minds quite easily go there. Others find sometimes visualizing things like this difficult. And all the more reason to work on that, that's something you should work on. Okay. Now, for those who didn't know when I mentioned it earlier, this is what's called isometric dot paper. If you've ever seen this before, notice the position of the dots. They're not in straight lines. They're kind of offset that way. This is often used to draw 3D objects, like this, right? Or this, okay? The paper can be useful for drawing things in 3 dimensions, okay? You kind of get used to it at first, but it's just a matter of connecting the dots to create those shapes. It's something you can use to draw things in 3 dimensions and help visualize things in 3 dimensions. Okay, now eventually this has to get to real world objects, right? So if I said sketch your house as if you were flying over it, and let's say this was kind of your house, you might draw something like this to kind of visualize it from that way. And again, this is an important skill set to have, especially if you're going into anything like construction, okay, or carpentry, is that ability to visualize things in 3 dimensions and then change the dimensional view. Super, super important. Okay, moving on. The fact is, though, for the most part, we don't need to be artists to do this stuff. Math allows us to use formulas to calculate some of this stuff. So if you're not the person who can visualize this stuff, and you're not the person who can draw this, math can be your rescue because it allows you to use mathematical formulas to calculate values. So the simplest formula is the area of a rectangle. So the area of the rectangle, I hope you know, is just the length times the width. So the 8 times the 7 gives me 56. That's an easy one, okay? I didn't even put a unit on that. I could have said 8 centimeters, 7 centimeters. Doesn't matter. Unit wouldn't matter. It's a simple calculation. Now let's move up a step. From the simple rectangle, we'll move to the triangle, okay? Now the triangle's a little more complicated. With the triangle, we need to calculate the height of the triangle. So you need to take a point on the triangle and go across to, let's call this ground area the base. So this part here, if the triangle's sitting on the ground at some point, and by the way, it wouldn't matter which way you'd have the triangle, but with one part flat on a theoretical ground, that length would be the length of B, the base. So the base here would be 6. But as well, you could draw a line here going up 4. That would be the height of the triangle. And the area is height times base divided by 2. So in this case, height times base, 4 times 6, 24, divided by 2, 12. Okay? Now, if you don't have this formula in your mind, that's fine. But that's what you're going to need to work on for this assignment today, is calculating areas of triangles. All right, let's move up a shape. Circles. Okay? Circles require the use of that symbol, pi. Pi is a magical number that works with circles. It's 3.14, etc. Okay? But with pi, we also need some other measurement with the circle. And in this case, what we're going to use is the distance from the center of the circle to the edge, which we call the radius. Okay? In this case, with the radius at 2 centimeters, I can plug the 2 into my formula. So r becomes 2, and now we know how to square things really well. So 2 squared is 4. Pi is 3.14 times 4. I get 12.56. Okay? So the area of that circle, 12.56 centimeters. Okay? Again, a practical application in all kinds of construction and things like that is calculating areas of circles. Okay. So those are all 2-dimensional objects. Let's kick it up a dimension. Let's take a prism, okay, which is a 3-dimensional object, okay, like as if we took the rectangle and added depth to it. So with the prism object, the formula gets a little more complicated. The formula for the surface area of a prism, and again, surface area means the area of all the sides, all 6 sides, is as follows. 2 times b, where b is the base. So you calculate the base area. And the base in this case is 4 times 2, right? Plus p, and p for this formula is the perimeter of the base. So the perimeter is the total distance around. Can anyone think what the perimeter of the base of this shape would be? Well, it'd be 2 plus 4 plus, what would this amount be? 2, right? And then this one, 4. So it'd be 2 plus 4 plus 2 plus 4, okay? And as well, you also have to multiply it by the height. You wouldn't have to worry too much about it. Yes?
Oh, I was going to say that it would be 8.
Okay, well, here, I've got the math here. So, yes, it'd be 8, and then the perimeter would be 12 times 1, 16 plus 12, 28, okay? And those are some pretty easy numbers to work with, okay? But the surface area of that prism, 28 centimeters. Now let's kick it up another notch. The last shape you need to know for your grade 9 is the cylinder, okay? Now the cylinder is the three-dimensional version of a circle. Although you could also say that a sphere is that. But with the cylinder, we're now going to change up the formula so that it's 2 times pi r squared plus 2 times pi r h. So now the other additional measurement we need is the height of the cylinder. But really we only need those 2 measurements, the radius and the height. And then we plug those into the formula. So we know what pi is, we know what r is, we know what pi and r is, and we know what h is. So we can just punch those in. And now, being comfortable with powers and with BEDMOS, we can start to work through that formula to get to your final answer down here. Okay? So the previous unit applies here in the sense that we can use our power knowledge and we can use our BEDMOS knowledge to work through the formula to get to the answer. Okay, let's kick it up another notch. Let's put it together. Here's the question, combining them. Now I have this weird shape. I have a prism with a cylinder on it. What's the surface area of that shape? Well, you have to think about that for a minute. Like, let's say you're a baker, and you were going to bake this as a cake, right? This is going to be your cake, but you wanted to put icing on the whole thing, including the bottom, which doesn't make sense, but let's say you did. You want to also ice the bottom of it. How much icing would you need?
Just if you were really a baker and you were making a cake with that much icing, just buy a ton and then just use it for the next cake.
Yeah, okay. But you could also, for sure, maybe you should look up hypothetical in the dictionary so you know what it means a little bit. Okay, this is just an example, okay? If you guys just want me to throw out actual problems, I will, because that's what your math tests are going to be. But let's again go back to the baker scenario. So you got to figure out how much icing is going to cover this whole thing. In other words, what's all the surface area? Well, here's what you know. If the cylinder wasn't part of it, if the cylinder wasn't there, you could use your formula to calculate the surface area of the prism. But you know that the cylinder's on it. So essentially just that area of the circle could be subtracted from how much you're going to use. Similarly, if the cylinder was on its own, you could calculate the surface area of the cylinder using the formula I just had. But because the bottom of the cylinder is touching there, I could also subtract the area of a circle from that. So what I'd first do is calculate the area of the prism. I'd get 28, right? Punching the numbers in. Then I'd calculate the area of the cylinder. I get 62.8 if I punch the numbers in there. Then I'd calculate the area of just that little circle, and I'd get 12.56. Now I could play with those numbers. I could say, okay, I'm going to take the area of the prism and subtract the circle. So that's like as if this thing had that circle piece removed. And I'm going to do the same thing with the cylinder. The cylinder as if one little circle was removed. And then I'm going to add those two things together. I'm going to add this and this together, and all those numbers will start coming together to give me 65.68. Okay? This is the kind of question that I've seen on the grade 9 exam. Okay? Is basically that question. So you need to be practicing this question. Okay? It seems maybe a bit overwhelming right now because you haven't practiced this stuff yet. Okay? It's practicing just using formulas. But once you get used to these types of questions, you'll get used to answering them. Okay? Okay, terminology. So once you see questions, and this is also going to happen in the textbook, you're going to see the way it uses these words. So I've got to make sure you're comfortable with them. So I'm going to go quickly through this. But when you have a line that goes from A to B, this is called a line segment. In math, we often write it like this. AB with a line over it. What that means is line segment AB. When we have a triangle like this, okay, triangles are often named by the three corners or the three sides, okay? They will often use a symbol like that, the triangle symbol, and say this is triangle ABC. They'll also name the angles. They'll say this is angle X. They'll use that little symbol to represent an angle, okay? You're going to see these in your textbook, so you got to be kind of aware of them. Now, another thing we do in geometry is we often put little check marks or ditto marks or tally marks on sides to indicate when they're equal. So what you're seeing here with these two triangles is you're seeing one check mark here and one there. That means those two sides are equal length. Doesn't matter what the number is, that side and that side are the same. Similarly, this one has 2 checks and 2 checks, which means those two sides. This one has 3 and 3, they're equal. Okay? Same with these ones. We can also do the same with angles, and there's 2 ways that that's sometimes shown. Sometimes they use those like just a little half circle, and then they'll use 2 or 3 of them. And then other times they'll just put the circle with a little check inside of it. Okay? I wouldn't worry too much about it because your textbook tends to just put numbers on things. But that can happen sometimes. Okay, couple more terms. The point where 2 lines meet in an angle is called the vertex. A median is a line drawn from any vertex to the middle of the opposite line. A bisector of an angle is a line which divides the angle into 2 equal angles. Good news, most of this terminology is not technically part of your grade 9 unit right now, okay? Used to be, it's not anymore, okay? Definitely will be for those of you taking either applied or actually you don't have that choice next year. Never mind. So, and I'm sorry guys, I wish this was a shorter presentation. With triangles, you guys need to know that triangles have names, okay? So I'm going to go quickly through this triangle stuff. Triangles have names like scalene, isosceles, and equilateral, okay? Scalene is one which has 2 sides, none of which are equal. Isosceles, 2 sides are equal. And equilateral, all 3 sides are equal, okay? As well, triangles are named by angles. There's what's called an equiangular triangle, which means all 3 angles are the same, okay? Of which they would always be 60. Okay? A right angle triangle means one of the angles is 90 degrees. At least, it can only be one, but one angle will be 90. Okay? An acute triangle, all the angles are less than right angles, and an obtuse triangle is one in which one angle is greater than 90 degrees. Again, just some terminology. I'm hoping that some of your math teachers in the past have introduced these terms to you. Okay. The basic theory with triangles is that if you add all the angles up, it'll equal 180, okay? Measuring angles with triangles is what protractors are for. But one thing you do need to focus on with this grade 9 is the concept of similarity. So that previous stuff, don't worry about too much about triangles. But this you do actually have to worry about. How do you know when 2 triangles are similar? And what does that even mean? So similar means they're alike in all ways except size. So they're the exact same triangle except one is bigger than the other or smaller than the other. So in order to figure that out, we got to kind of do a little math on that, okay? The symbol for similarity is that thing there called the tilde symbol, okay? It means similar. If it was the same, they would use an equal sign there, okay? So here's 2 examples. This is 2 different triangles, but they are considered similar triangles. They are the same in every way except size. So in other words, these angles will be the same, okay? But the size will be different. But the size is a proportion to the other triangle. Okay, so how do we detect this? Well, we detect this in 3 different ways. First way is called angle-angle. If 2 angles match on a triangle, then they're similar triangles. So all I have to do is measure this angle and compare it to that one. Oh, they're the same angle. Then I'll measure one other one. Measure that angle, measure, good enough. I don't have to even go to the 3rd angle. they'll be similar at that point. So the first condition is called angle-angle. If two angles are the same, you have two similar triangles. They're basically smaller or larger versions of each other. Second way you can detect it, it's called side, side, side. With this one, obviously the sides aren't going to be the same length. This one's 5, this one's 10. This one's 5, this one's 10. This one's 3, this one's 6. But what do you notice about the relationship between the sides?
First triangle is always half the second.
Yeah, this one, or you could say this one's double the size, right? 5 times 2 is 10. 5 times 2 is 10. 3 times 2 is 6. What we're looking at there is a ratio, okay? The ratio in this case is 0.5. Now, what you're going to need to do is work on this as well, as how this actually works with ratios. So I'm giving you a lot of talk today. So most of this I'm going to try and do an example tomorrow for you. The third way is called side angle side. This is a mix of the other two. So this one you just measure one angle and two sides, but the two sides have to be the sides that are touching that angle. So I can measure this and the two sides and this and the two sides. Now the two sides aren't going to be equal, but they're again going to be a ratio of the other one. Okay? So we'll work on that a little bit tomorrow. But those are the three ways. Angle, angle, side, 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 angle, side. Okay. So the way you're going to work on this is you're going to measure, and then you're going to basically plug it in and check to see if it meets the conditions. Okay? All right. So now we have these triangles, and they're similar. What can I do with them? What's the point of this? Well, similarity, again, similarity means similar to, right? So if the two triangles are related to one another, we can actually use them to solve interesting problems. Okay? So these ratios, and by the way, ratios are essentially fractions. Sometimes they're written with that little colon in between. Sometimes they're just written or spoken as the ratio of A, B, etc. Okay? Again, we'll work a little bit on that tomorrow. But using ratios, you can actually figure out some interesting problems. Okay? So for example, I can figure out what the side x is, even though I don't know what it is. Because I can use ratios to calculate what x is. And I can use a method called cross multiply, which maybe I'll go into more detail for sure tomorrow. Okay, I want to try and wrap this up. So I'm going to try and pull it together with polygons. Believe it or not, your actual grade 9 curriculum goes beyond triangles to the concept of polygons. Poly means many in Greek, and gon, again, means angle. So it means many angles, right? A polygon is any shape that's enclosed that has more than three or more sides, okay? So a triangle is a polygon, believe it or not. A square is a polygon. But these are also polygons, all the ones you see here. They're any shape with multiple sides beyond 3 that's enclosed. That's a polygon. Okay? Polygons are said to be similar if the sides are proportional and all the angles are the same. All the angles. Okay? So this would be an example of two similar polygons. They have all the same angles. And although their sides aren't the same length, they're a proportion to one another, right? So this polygon is twice as big as this one. Because if I take 3 times 2, or if I take 2.3 times 2, I get the same number there, okay? So you're going to have to kind of figure that out with the types of questions you're going to be encountering with this. Okay, so I have an example here of how that's done. You can calculate through it. And again, I'm going to try and go through that in slower detail tomorrow. Okay, now, here's the thing about polygons. Polygons, which are these closed figures, can actually be turned into just triangles. I'm going to show you that right now. Here's 3 polygons, and you can actually turn them into triangles that don't overlap with one another. And for those of you boys or girls in here who are interested in video games, by the way, that's actually how the Xbox and the Xbox 360 works. All it does is does calculations with triangles, because you can use triangles to build more complex polygon shapes. So actually studying the triangle as a shape is another sort of geometrical way that you can go beyond even just studying it just for study's sake. Okay? All right. Whew, we've reached the end. It was a lot of stuff, but here's what the actual curriculum needs you to do. It needs you to know those area formulas. Okay? That will be in your notes. So your notes are actually very short. It's just this, and this concept of polygons and how similar polygons are. We're going to push the triangle stuff aside a bit for today. We're not going to worry about it. I introduced it to you. It'll come back, but right now we're going to focus. Because look, moving ahead, really, this is what you need to take from today. Area, surface area, similar. 3 things. So now it's simpler. Wow, Walks talked for 40 minutes just to give us 3 things. Because your curriculum says this. It says, figure out the surface area of a 3D object, specifically a composite 3D object, which means 2 objects put together, like that cake thing I was talking about. And then it says, demonstrate an understanding of similarity of polygons. So how are 2 polygons similar? Okay? So, with that nasty presentation done, I'm going to now show you what I'm going to give you for an assignment to work on with this. You will have the remainder of the period today